Welcome back. Today's second talk will be given by R Ganapati, and she will be speaking on Kasdan isomorphism and its variants on general connected reductive groups.
Yeah, thank you. Thank you for the invitation to speak in this conference. So I will talk about this work of Kasdan and which was done for split groups. I'll talk about a variant of it and its generalization, the generalization of these two results to non-split groups. Okay, so I'll begin with a review of the work of Deline and Kasdan. Okay. Okay, so I'll fix some notation. F is a non-Archimedean local field. OF is its ring of integers. F is its maximal ideal. I'll fix a uniformizer, omega F, and a script K sub F is its residue field. And Fs is a separable closure of F. Gamma F is the gamma group of Fs over F. If is the inertia group of F. And If to the m is the mth upper numbering filtration. Filtration of If. Okay. So recall that two non-Archimedean local fields, F and F prime, are M close if OF mod PF to the M is isomorphic to OF prime mod PF prime to the M as rings. Okay. And one can note that given F prime of characteristic P and M greater than or equal to 1, we can always choose F of characteristic 0 such that F and F prime are M close. You just have to choose the field F to be ramified enough such that F and F prime are M close. Okay. So Deline proved the following. If the fields, if F and F prime are M close, then gamma F mod IF to the M is isomorphic to this quotient over the other field. I'll label this as the Deline isomorphism, and he explains the idea in his paper at the start. I'll just say how it is, what he has said. So for example, so suppose L over F is a totally ramified extension with such that I of L over F to the M is 1, then L is F of alpha, where alpha is a root of some Eisenstein polynomial. Alpha is a root of an Eisenstein P of x, which is x to the n plus say omega f some ai x to the I. Then let ai prime in OF prime, this is the other field F prime which is M close to F, be such that ai prime mod PF prime to the M is ai mod Pf to the n under this, under this isomorphism, and then let L prime be defined to be the root of the polynomial p prime of x, which is now x to the n plus a uniformizer f prime, which maps to the class of the uniformizer of f under this isomorphism, some ai prime x to the I, and L prime is f prime of alpha, where alpha is a root of this polynomial. That's how you construct this extension L prime over f prime. There are many things to check here. So, for example, I think he shows that if this does not depend on the choice of AIs using this condition. So this is how this is the idea of the proof of this isomorphism of Deligne. And this is for Galois groups. A similar story, which is for representations of PID groups, is due to Kasdan. So I'll recall Kasdan's theory as well. So let G be a split connected reductive group over Z, and then set G to be G of f, and Km is the kernel from G of OF to G of OF mod Pf to the m, and you fix a Haar measure on G, and he looked at this Hecke algebra H of GKM, which is the Hecke algebra of Km bi-invariant functions. So this is the span of the C span of 1 over volume of Km, the characteristic functions of Km, GKM, G in G. Now, the first thing to note is, so G of O, if f and f prime are M close, then G of O mod Km is isomorphic to G of O prime mod Km prime. This is the first, and then you also have a Cartan decomposition of f is the disjoint union of lambda in x lower star of t minus, I didn't say what t was, you fix a maximal torus that z split in z, and then this is the, and then so this is G of OF lambda of, so you have the Cartan decomposition, and combining these one gets that if the fields f and f prime are just M close, you get this leads to a bijection, an isomorphism of C vector spaces between these two Hecke algebras, H of GKM and H of G prime Km prime. I didn't say what Km prime is. Km prime is just the corresponding object over f prime, and then a third input here is that this Hecke this is due to Bernstein. This Hecke algebra H of GKM is finitely presented. So combining this with these observations, Kasdan proved that given given m greater than or equal to 1, there exists L greater than or equal to m, such that if the fields f and f prime are L close, then the Hecke algebras H of GKM, I mean, this map of C vector spaces is actually an algebra isomorphism. H of G prime Km prime is an algebra isomorphism. Okay, so there is, I'll just mention it here, there is also a variant now for the Kasdan isomorphism. I'll spend more time with this variant later in the lecture, so I'll just mention it here. This also holds if Km is replaced with the mth Moy-Prasad filtration of an Iwahori subgroup. Moy-Prasad filtration of an Iwahori subgroup. Okay. Okay, so I'll erase this if that's okay. I hope everyone has noted this down. There are 2 postdoc talks in the afternoon and a talk by Professor Premi Chandra. Is it okay? Okay, so what this leads to is the following. So if f and f prime are sufficiently close, then you can look at this picture. So on the one hand, so this is the Weil-Deligne group of F, and you look at the so this is the L group of G, and you look at the admissible homomorphisms from WDF to LG, whose depth is less than or equal to M. On this side, depth is defined using the upper numbering filtration of the inertia, and then you have a map from WDF prime to LG such that depth of, I've said sufficiently close. I'm not saying it's M exactly. It could be larger. I mean, as in, okay, in Kasdan you don't, Kasdan had conjectured that you can take L equals M, which is now proved. But when you do this for non-split groups, you might have to assume that the fields are closer to get results at level M. Okay. Okay, and then similarly, this you have, this is due to Deligne, and similarly you have sigma, you look at irreducible smooth representations of G of F, such that depth of sigma is less than or equal to M, and then via the Kasdan isomorphism or its variance, you will be able to so sigma irreducible representations of sigma prime of G of F prime such that depth of sigma prime is less than or equal to M, and then okay, I'm implicit in this is I'm assuming that some kind of depth preservation result holds to even put together this picture, but I'll not get into that today. So I have this, and then one can look at the commutativity of the diagram if the Langlands correspondence is known both in characteristic P and 0, or if it's known for all local fields of characteristic 0, then this method can be used to prove the Langlands correspondence in characteristic P. So I'll state a few things that have already been done. So characteristic of F, so assume characteristic of F is greater than 0, then Enya, use this approach to prove the numerical Langlands, the numerical local Langlands for GLN. Bardulescu proved the Jacquet-Langlands for GLN using this method. So he had to generalize the Kasdan isomorphism to inner forms of GLN in the process. And in my thesis, I had looked at this question for GSP4F, where F is of positive characteristic. So this was used, this method was used to prove the local Langlands for GSP4, provided P is greater than 2, the characteristic is greater than 2. And then in joint work with Sandeep Verma, we looked at split classical groups and P it's too small, sorry, okay, I'll write bigger. For split classical groups and P, some restrictions on P, so I'll just say P large. This method was used to prove the, was used to transfer some of the work of Arthur to characteristic P. So, as I said, this is for split groups, so I want to discuss the question of generalizing the work of Kasdan and its variant that I did not go into to non-split groups. Okay, so beyond split groups, so the first, there are a couple of issues. I'll say a bit about everything. Okay, first, given a split G over Z, you can work with this group over an arbitrary field after base change. You can work with G of F for any field F. But in general, if your group is not split, then one first has to make sense of what it means to give a group G prime over F prime, provided the fields F and F prime are closed. And then you also have this isomorphism. G of O mod Km is isomorphic to G of O prime mod Km prime if F and F prime are M closed. And again, when G is not defined over Z or over O, then one has to resolve this as well. So I'll say a few words about this. Okay, in the general setup. So over, because I'm not going to spend much time with these two results, so I'll just say what, okay, over F prime. So given a connected reductor G over F that splits over an at most M ramified extension, by that I mean it splits over an extension L over F, where L, which has the property that I of L over F to the M upper numbering filtration is 1. And so I want a G prime, again splitting over an at most M ramified extension. And then, let's say S is a maximal F split torus in G. Then you can look at the apartment of A of SF and facets there. And similarly, I want to pick up a maximal F split torus, F prime split and an A of, I want to look at A of S prime, F prime, and then I have a phase set omega prime here. I want to understand how these correspond. And then you can look at the parahoric group scheme P omega. Constructed by Brouhatitz, and then you also have a P omega prime, and then one would like that P omega, which is defined over OF a priori, cross over OF mod PF to the M is isomorphic to P omega prime cross over OF prime mod PF prime to the M via this isomorphism of rings to be an isomorphism of group schemes, and then as a consequence of this, one gets that P omega of OF mod PF to the M is isomorphic to P omega prime of OF prime mod PF prime to the M. Okay, and that and the two isomorphisms that I mentioned there, that K mod Km is isomorphic to K prime mod Km prime. When the fields F and F prime are sufficiently close, here K will be a special maximal parahoric. Okay, so yeah, I'll write it next. What is the? I don't understand the question.
P omega x OF.
No, it's not x. It's a scheme over OF. I am base changing it to OF mod PF to the M. Okay, so as a consequence of this, one would get that K mod Km is isomorphic to K prime mod Km prime if F and F prime are sufficiently close. So here K will be a special maximal parahoric. This will play the role of G of O in the Kasdan isomorphism. You can also prove, this will also show that I mod Im is isomorphic to I prime mod Im prime. Again, if the fields are sufficiently close, here I is an Iwahori subgroup. So this is the parahoric subgroup attached to an alcove, and then Im is the kernel again of this group scheme I of OF to I of OF mod PF to the M. Okay, so this has been done. This is complete. So I'll just explain the idea for a sketch for the quasi-split case. Okay, so I mean the idea is simple. So if you're say given a unitary group, so let's say F and F prime are M close, and you're given a unitary group over F that splits over a quadratic extension E of F that is at most M ramified, then what you want to pick up the unitary group over F prime, where E prime over F prime is the extension constructed by Delhi. That's all is there here. So I'll just write it down formally what this means. So G0 split with based root datum, say R0 delta 0, and then I'll take a pinned group, so I'll have G0, B0, P0 and delta 0. Oh sorry, not that, sorry, X alpha alpha and delta 0. And then we know that the F forms of G0 are parameterized by the pointed cohomology set H1 of gamma F and aught of G0 Fs, right? And the quasi-split F forms of G0 are in the image of H1 of gamma F R0 delta 0 to H1. I mean, there is a okay, yeah, there is a splitting. I'm not going into all the details, but okay, H1 of gamma F and aught of G0 Fs. So if you want to, so now if you want to look at F forms of G0, that split over an at most M ramified extension of F. Then one can easily show this. This is parameterized by this set H1 of gamma F mod IF to the M aught of G0 Fs. Okay, and similarly, if you look at the quasi-split forms that split and become isomorphic to G0 over an at most M ramified extension, then this lies in the image of H1 of gamma F mod IF to the M and image of automorphisms of this based root datum inside in here. I'll just write. Okay, so now it's clear or it's easy to show that using the Deligne isomorphism you have an isomorphism of these quotients, and the group is split over Z, so you can think of it over F or F prime. This is the same, and then this proves. So use Deligne to show that and you can look at this over the field as well. Okay, so F prime, and here F and F prime are M close. Okay, and okay, so with this isomorphism you'll also be able to further you start with the pin datum, so this will give you both GBTS. This is a quasi-split connected reductive group over F with a Borel. This is the maximal torus, and this is a maximal F split torus sitting inside T, and you will also get this via this correspondence. You will get this G prime, B prime, T prime, and S prime, and then a simplicial isomorphism between the apartments of A of SF and A of S prime F prime. And then once you have this, you can look at facets here that will correspond to facets here, and so you can look at the parahoric group scheme. So this will say could correspond to omega goes to omega prime. And then the theorem is that P omega cross over OF mod PF to the M is isomorphic to P omega prime cross over OF prime mod PF prime to the M, okay, OF prime, where I am going from this to this via the isomorphism, say phi M from this is an isomorphism of group scheme. So in particular you recover that P omega of OF mod PF to the M is isomorphic to P omega of OF prime mod PF prime to the M. So this resolves the first issue that I had mentioned. So using this, I wrote down the idea only for quasi-split groups, but this works in general. And using this, one can show that. So using this, the Kasdan isomorphism holds for general connected reductive groups where G of O is now replaced by a special maximal paraphoric subgroup. Okay. So I next want to go into this variant of the Kasdan isomorphism. No, there is no. This is a simplicial isomorphism. So whatever I pick up a special vertex here, I will get something. Okay, so I want to talk about this variant of the Kasdan isomorphism. I'll again explain what is known for split groups. So so again say G is split with I'll assume it's pinned with G. And then I'll take I to be the standard Iwahori subgroup. I fixed a Borel, so the standard Iwahori subgroup. So this is, if you want to write this down explicitly, this is generated by U alpha. These are the root subgroups, U alpha O, P of O, and U minus alpha P, where alpha is in phi plus is in the set of positive roots, and then I will look at the nth filtration of the Iwahori, which is IM, which we'll denote as IM. So this is U alpha P to the M, and then I have PM, and U minus alpha P to the M plus 1, again alpha in phi plus. And then it is this is known due to Brouhatić that G is the disjoint union of W in W, IWI, where W is the Iwahori while group. Sorry. So we know so this looks like you have W of, so this decomposes as W affine semidirect product with omega. So this this is a Coxeter group, so this is actually W affine and S affine, and this is the set of length 0 elements in W, so these are the elements that stabilize an alcove, and omega is the set of length 0 elements in W. And another decomposition of this, which is also is that it decomposes as X lowest RT semi-direct product with W0, where W0 is the finite while group. Okay, but with this and so for example, if you want to look at GLN, I'll say what it looks like for GLN plus 1. This is the case that Roger Howe had looked at. Okay, so for GLN plus 1, W affine is generated by say S0, S1 through Sn. These are the finite simple reflections for GLN. So Si is SEI minus EI plus 1, 1 less than or equal to I less than or equal to N, and this S0 is this affine simple reflection, which is 1 minus E1 minus En, and this group omega is actually isomorphic to Z, and it is generated by the element it's T En plus 1. This is the translation, and times S1 through Sn. This is how it looks for GLN plus 1. Okay, and so we Roger Howe considered this Hecke algebra. Consider H of GIM so we have so recall that I have already chosen a pinning X alpha, alpha and delta. So one can so then you have your W affine. So W affine is generated by these reflections. So W affine, S affine is a Coxeter group, and S affine has some finite simple reflections. Say what is my notation? Okay, so S0, this consists of the finite simple reflections, and I mean I have made a choice of a base point, and then I have a this is a finite simple reflections, and these are the affine simple reflections that okay, and then I can look at S affine minus S0. This consists of affine simple reflections. Okay, so then with the choice of the pinning we have, so for S and S0, so I'll write it as say SA for a finite root SA. Choose, I mean there is a standard choice of representatives once you make a choice of a pinning. So NSA is XA of 1, X minus A of minus 1, XA of 1. This is this is actually in the normalizer of T. So this is so this is in G of F, and for the affine simple reflections for SA in S affine minus S0, NSA is just B check of omega F times NSB. Here B is the gradient of it. So once you make a choice of a pinning, you do have a natural choice of representatives for your affine simple reflections. Now I'll state a few facts. Then lemma 1, the NS, so recall that I am still in the split case. So I'm only recalling what is already known right now, because for non-split groups, this some of these don't go through. So G split here. I'll point out when I transition to non-split groups. The NSA, SA and SS is affine, satisfy Coxeter relations. So this is analogous to what happens for the finite while group. And then 2 NSA square is B check of -1, where B is the gradient of A. And so now, and then for tau and omega, so I have already explained how to pick representatives for the affine simple reflections. I have to tell you what to do with omega, but you do what is obvious. So okay, so for tau and omega, write tau as T lambda times W, where lambda is an x lower star of T and W is in the finite while group. Note that because the NSAs satisfy Coxeter relations, for any W, this condition 1 will give rise to a set of representatives NW, W and W0. I mean, of course, for this is actually for the affine while group, but in particular it also gives it to you for the finite while group. Because these conditions will tell you that it doesn't matter what choice of reduced expression for W you have, the representative is the same. And then you choose n tau to be n lambda times nw. Then so then I'll recall a theorem which is due to how for GLN and for split groups. So I'll not write down everything because there are many relations. I'll just write down the ones that I need for the rest of the talk. So I'll denote Fg to be the 1 over volume of Im times the characteristic function of Im, Gim, for G in G, and G for split groups. The Hecke algebra, each of GIM is generated by one F NSA in S affine, 2 F n tau and F n tau inverse, tau in omega, and FB, say B in I mod Im, subject to a bunch of relations. I'll just recall a few of them, subject to A, the F NSA satisfy Coxeter relations. But I mean, this is not precise, but I hope it's clear what it means. Coxeter relations. And then you can look at the square of the element, FNSA. You can convolve it with the same element. And then this is FNSA square. And then you have some some Q times some sum, which is in SA I M SA inverse mod IM of Fx. This part is not important, it's just that this shows up. And then I'll state a few more just to motivate what comes next. I'm not stating all the relations. F n tau. So omega stabilizes the alcove, so it permutes the finite simple reflections that form the walls of the alcove. So you have a relation that comes from that. So this is F S N star F n tau inverse. So there is some C of S tau that shows up. This is some order 2 element, so I'll write down what this is, okay, star. So this is actually in T of O in this case, an order 2 element. So when you multiply the representatives for the elements of the while group that are not length additive, some collapsing will happen and you will pick up some order 2 elements. That's how this shows up. And F n tau prime is some C of tau prime, say again, convolved with F n tau prime. I'll just remark that again this is this lies in T of O, order 2, and it shows up for the exact same reason as before. And note that this, I mean, if the Corpus homomorphism admits a group theoretic section, this factor would not show up. But it's not known in general that the Corpus homomorphism admits a group theoretic section, so that is there. And then these relations show up. So I just wanted to point out that these are there. And then theorem, which is due to Lemay for GLN, and then I did it for split groups, is that if F and F prime are enclosed, then H of G IM is isomorphic as algebras to H of G prime IM prime, provided and it in fact matches these generators. Recall that I had fixed a pinning, and then I can use over Z, so I can use the same thing over F and F prime, and then I have NSA F NSA goes to F NSA prime, and so on. So it matches the generators that we have constructed. Okay, so sorry? FB and whatever, yeah. So this is in the normalizer of the Iwahori, so there are some relations that come from that as well. Yeah, there are a few more. Okay, so I'll just mention some consequences of this, of this theorem. Because you're able to write down an explicit presentation for this Hecke algebra, transferring properties over closed local fields, there's a technical advantage of using this isomorphism over the Kasdan isomorphism. So one of the consequences of this theorem is that, so of course you have a bijection sigma irreducible representations of G of F such that say sigma IM is non-zero, and then you have a corresponding irreducible representation of G of F prime such that sigma prime IM prime is non-zero. One can show that this bijection preserves the genericity. It preserves L and epsilon factors of pairs coming from the Langland-Shahidi method. So I should mention that part of this is actually due to, so this is Mian and Louis Lomeli. And then, so then this played a role in proving that improving the local Langlands for both GSP4 and for split classical groups. So then, if you look at, so what does this mean? Okay, so to generalize this result, so to generalize theorem 1 to non-split groups. We need one, the set of representatives in SA, SA and SFN that satisfy Coxeter relations. And so yeah, that's the reason I wrote this. You do want to have control over this. It's okay if it's not of order 2, but nevertheless, remember that this lies in T of O, and T of O lies in the Iwahori subgroup. And the way FB goes to FB prime is via this isomorphism. So you do want control over NS square, the C of S tau, and C of tau tau, right? So another way to, in fact, if this is an element of order 2, usually this is, right, at least in the split case, this is of this form. So the question one is asking is, can one construct the Titz group of the affine? So can one construct a Titz group for the affine or Iwahori-Weil group? So I'll mention some results in this direction. So what one means here is that, so we want groups, Titz groups T affine and T sitting inside G of F, such that with S2 to be B check of -1, B in phi. This is now the relative root system. I'm not saying it precisely. So 1 S2 goes to T affine, goes to W affine, goes to 1, and then this embeds into the Iwahori-Weil group. And where T affine is generated by, say, these NSAs. Then, so I'll state a theorem. Okay, this is joint with Schumacher. So if G splits over an unramified extension of F, then the Titz group T affine and T exist. I don't know if I'll have time to say anything about the proof, but I'll remark here, we had observed that for the even unitary groups U6 contained in, say, restriction L over F of GL6, where L over F wildly ramified, the Titz group T affine does not exist. A group with these properties does not exist. But at that time, I think we didn't have clarity on what exactly was going wrong, so I'll end with one more result. Theorem. Yeah, so let G be a connected reductive group over F, such that, okay, so I'll say what this is. Does not contain a simple factor of unitary type. I mean, it does not contain a simple factor that's an even or an odd unitary group. Then the TITS group T affine exists. This is the first part. Here F brev is the completion of the maximal unramified extension. So once you go to F brev, the group is quasi-split. So we are saying that it does not contain a quasi-split even or odd unitary group as a simple factor. Completion of maximal unramified extension. Part 2. If G is, say, restriction L over F, restriction of scalars of an odd unitary group, we do have representatives that satisfy Coxeter relations but the affine TITS group does not exist in general, meaning so when you place this restriction about how the square of this element is of this form, this doesn't hold for odd unitary groups, and if G is an even unitary group, sorry, I forgot to say that this is when L over F is ramified. Of course, if it's unramified, it's already covered here. When G is L over F, restriction L over F of U to N, L over F ramified, any ramified extension, oh, not L over F, sorry, I'm messing this up. I mean, the quadratic extension defining the unitary group is ramified. The unitary group is a ramified unitary group. Here again, U to N ramified unitary group. There do not exist representatives of affine simple reflections that satisfy Coxeter relations. There exist no representatives in G of F that satisfy Coxeter relations. I'll just end with one remark. The non-existence of the TITS group here doesn't say that such an isomorphism cannot exist. It's just that in those cases the result may not be as clean, and there may be some relations which are not as nice and elegant as these places. Yeah, I'll stop.
Any questions?
Yes. Yes, and making sure that the generators match to generators with an exhaustive set of relations. This is the obstruction to that. Yeah.
Yeah, from the special maximal case, can one go deeper?
So, yeah, you can show that there exists an isomorphism of these Hecke algebras. Again, the same strategy of Kasdan, because these are still finitely presented, and you have this isomorphism of points, and then, yeah, so one can still do that. But if you look at these proofs of, say, genericity and L and epsilon factors of pairs, you actually explicitly study the generators that we had listed on the representation and transfer those. So to do that, you do need a nice generating set for this Hecke algebra, which matches with a nice generating set for this Hecke algebra.
But parabolic induction is okay? Or
Parabolic induction is okay, yes.
And discrete series to discrete
series? Yeah, discrete series, supercuspidals, they are all okay. Genericity, L and epsilon factors of pairs, those are the troublesome ones. Yeah.
Thank you.
Yeah.
Any other questions? I have a question. Is the presentation true over, let's say, Z with Q inverted?
Yeah, this will be a presentation over Z actually. Yeah, I mean, yeah, you could invert Q, but it will be a presentation over Z. In the case where it is known, in this work with Shua, it is a presentation over Z.
So, If there are no further questions, let's thank the speaker. So we take 5 minutes break and